All right, hello everybody. First of all, let me apologize for not meeting with you today. But I am not feeling well and I don't want to share this with the rest of you. So please bear with me while I try to walk you through Lab0 remotely. So with Lab0, what you're going to do is you're going to build what we're calling a bitmap filter. And all this is it's a program that'll take in a bitmap image and apply one of three possible filters to it and then output the result. So allow me to demonstrate. So here I have my version of this project, and the name of the executable that I'm creating is called BMP filter. And in the folder that I'm working with, I have a few sample bitmap images. So for instance, there's an apple and a picture of some corn and a really silly, simple little face here. This is a really small file, so I'll zoom in on it so you can see my amazing pixel art of a little guy with a goatee. Okay, so let's demonstrate this. So the way this program works then is that when I run it, if I just try running it, I'll get yelled at. So it will tell me how I'm supposed to use it. I need to give the name of the executable, an input file, and then a filter flag, and then it lists the possible flags. So your program will need to do the same thing. If it's not invoked properly, then it needs to print a usage message, including the description of the flags that could be used. So I'll run this properly this time, bitmap filter, and we'll run it on apple.bmp. And the first filter I'm going to run is the grayscale filter. Okay, now, once it's done its thing, it will have output the results of applying the filter to a new file called filtered.bmp. And you'd see I had run it before, so I already had a file of that name. It's fine to just stomp on it each time you run it. And now you see that the apple image has been turned to a grayscale image. Okay, now I will run the threshold flag, capital T. We'll talk about each of these filters in a moment, but this is the threshold option. And you'll notice now that the apple has been converted to a black and white image. And finally, S for scaled. So you can't immediately see that anything happened over here, but when I open the file, you'll notice that it is half the size in both width and height as the original image. So that's how your program needs to function. Let's jump over to the lab spec here and talk about the details. So please don't use this video as an excuse to not read the lab spec. There's a lot of information here you need to understand, and I just want to hit some of the high points to get you moving. Firstly, there's some background information talking about the bitmap image format and how that it's laid out. You already have experience reading files as bytes and printing that information to the screen. So this is going to build on that. You need to be able to read in bytes, interpret those bytes, work with them, and then write them back out to a file. The BMP or bitmap file format is a standard file format that we can use for storing images in different ways. We're going to use just one of the ways that a bitmap can be formatted, and it's probably the simplest way. And again, read through these passages, but what I want to draw your attention to is the fact that a bitmap image file contains what's known as a header. So the first several dozen bytes in the file, when we open it and start reading it, are not the image itself, but rather information about the image. Information that will tell the program that's trying to open the file how to read the bytes that represent the image and interpret them properly. So our files will contain three main things: a BMP header, which will always be 14 bytes, and a DIB header. And the size of that can depend on the header type. We're going to use one specific header type we'll talk about in a moment. Then there may be some other stuff, even empty space. And by empty space, we just mean bytes that are present in the file but aren't storing any meaningful information for us. But at some point after the DIB header, the pixel array begins. Now I emphasize this point because we don't always know how much junk, if you will be between the DIB header and the actual pixel array. And so this is some of the information that we have to get out of these headers at the beginning of the file. Okay, now why would there be quote-unquote junk? Well, by junk I just mean data that's not part of the image. Our company might have a BMP image generator program that puts information, text-based information, for instance, about the image in the file at this location or something. So it could be used in various ways. The point is that the standard says the pixel array doesn't have to begin right after the DIB header, but the information about where to find it needs to be contained in these headers. So let's look at each of these three things: the bitmap header, the DIB header, and the pixel array. So first, the bitmap header. This will always consist of 14 bytes divided into 5 fields. And by fields, we mean sets of bytes that represent a specific type of information. Okay? For our purposes, the first 2 bytes will always contain the ASCII characters BM for bitmap, and the next 2 fields we're concerned with are the size of the file in bytes. All right, now you'll see that next will be 2 2-byte fields that are both reserved and application dependent, and we're not going to care about those. Now, when I say we don't care about them, that doesn't mean that we don't need to read them and write them. That means that we won't be doing anything with that information in terms of processing in our program. So you'll need to read them, and you should save them to write them back out, but you don't need to worry about doing any math or anything like that with them. And finally, the offset for the first byte of the pixel array data. So again, there's this notion that this pixel array is somewhere further down in the file, and here we're going to find information about where it is. Now, this offset is relative to the beginning of the file. So it's not how many bytes past the DIB header, but rather how many bytes from the beginning of the file down to the beginning of the pixel array. Okay, so make sure to read through that and be comfortable with it. The next set of bytes will be the DIB header, and the DIB header we're going to use, again, there are a couple of different types of DIB or device-independent bitmap headers that can be used. We're going to use the bitmap info header, and it has a very specific format, and here that format is described. So it's a little small on my screen. You're going to want to open it up and look closely at it. Okay, now again, this particular header, it's always going to be the same size. In this case, it'll be 40 bytes. So as you read through this, you'll see that some of these bytes are always going to be the same, and you can treat them accordingly, but others are going to vary from one image to another. So you've got to make sure that you read this data in properly, that you know when and where you need to process it, and that you're able to write it back out to a new file correctly. Okay, now you may notice that I'm kind of talking about the information in this file in stages, and I would recommend that when you write your code to process the information, you also do that in stages. Don't try to just pull things in willy-nilly. Go through steps. First handle the header, the BMP header, then handle the DIB header, and so forth. Okay, pixel array. So this is where the actual meat of the image lives. And again, read through these paragraphs, but in summary, the pixel array stores triplets of bytes that represent pixels, each pixel being represented by RGB or red, green, and blue values. Now, it turns out that the order these will actually be stored in the file is blue, green, and red. So make sure you have that correct in your mind and deal with it properly. The pixels do not start, I emphasize, do not start in the upper left corner of the image and read left to right and top to bottom like we might expect. Rather, pixels are stored row by row, starting in the lower left corner of the image, reading left to right and bottom to top. So you'll notice pixel 1, which is all zeros because it's completely black, is located right here. Next comes pixel 2, which is all white, which is represented by all of the 3 color values being turned all the way on at 255, and so that's this pixel here. Here's pixel 3, 4, 5, 6, 7, and 8. Okay? So left to right, bottom to top is the way that that the image will be stored. You need to make sure you process these images in the proper order, because if you don't, you'll end up applying some of the filters we deal with incorrectly, and your results won't match ours, and you won't get all your points. So make sure you do that in the right order. Okay, pixel row padding. So an important point to note about the pixel array is that each row stored in the file is required to occupy multiples of 4 bytes. Now, as we move through the semester, that'll become more significant to us. It's very common to do things in sets of 4, and that helps with efficiency when the computer is actually reading and writing memory. And so having a file format that requires things to be grouped in this way isn't actually all that surprising. So each row must have a multiple of 4 bytes in it. Now, if each pixel only requires 3 bytes, then you do a little quick math and you realize that, that's not always going to be a multiple of 4 bytes when we're finished. Okay, and so the way we'll have to deal with that is by putting in some padding, some extra bytes in the file that will be read but are not considered part of the image data itself. So, as a quick example, if an image were 8 pixels wide, as is shown, let's see, did I say above? Okay, I said if it were 8 pixels wide, I need to correct this little typo. This is only 4 pixels wide, I can count. All right, so if the image, here we say 8, it'll work for 4 as well. If it were 8 or 4 pixels wide, 3 times 8 is 24, or 3 times 4 is 12, both of which are multiples of 4, so no padding would be needed. On the other hand, if an image were 2 pixels wide, then 3 bytes per pixel times 2 pixels equals 6 bytes, which is not a multiple of 4, so padding would be needed. So in this case, after the pixel data on a row, we would have to inject padding. So here you see we've inserted 2 extra bytes that brings the number of total bytes in that row up to 8. Now again, the value stored in those bytes is not important and can be set to 0, which is what we've shown here. Okay, so you can get more information about the BMP standard by following this link to Wikipedia. There's quite a bit of useful info about it. Please, please, please read the spec and read it as soon as possible so that you can get a lot of those relevant details just from reading it. Okay, your task again is to create a command line tool called BMP filter, as you saw me using mine earlier, that will apply 3 different filters: threshold, grayscale, and scale down. So for threshold, each pixel in the image is going to be converted to black or white based on the average, based on the average intensity of its 3 color values. So if the pixels in the original image with an average intensity of 128 or more will become white, and those with an average below 128 will become black. Now, a quick note, remember that integer arithmetic can and will result in overflow and truncation errors when performing addition and division, especially because we're working with small values. So if you're using an 8-bit data type, please be aware that if you're adding together, for instance, 3 values that were at 128, what's going to happen if you store that in an 8-bit variable? Okay, so there's some data loss that could happen there if we're not careful. And then furthermore, we might be tempted to do things like add and divide, add and divide, add and divide when computing the average. In other words, dividing each time that we add. And that has ramifications in terms of error, because when we do integer division, realize there can be truncation, and so truncating 3 times, for instance, is worse than truncating once. So you're going to want to take steps to eliminate overflow and minimize truncation error when you compute your averages. And there's a little hint there about what to look at in doing so. All right, for the grayscale filter, again, so that was threshold, so it basically turns the image into a black and white image. Grayscale, we're going to do a similar thing. We're going to average together the RGB values for a pixel, but then what we're going to do is then assign in the new image the red, green, and blue values to be equal to the average for that pixel. So instead of setting the 3 values to all zeros or all 255, we're going to set all of them to the average of the 3 values in the original image. Again, pay attention to arithmetic. Okay, scale down. This is the trickier one, and so we suggest you start it last. This is going to scale an image down to half its dimensions in both width and height. We'll give you some examples. So if it's 100 pixels wide and 50 pixels tall, the result should be 50 pixels wide and 25 pixels tall. All right, now in general, that's going to mean that a 4 pixel square, or 4 pixels in a square pattern from the original image, become a single pixel in the filtered image. Now, I should point out also here that you're only going to use pixels from the original image one time in computing the values of a pixel in the filtered image. So just think of using a box of pixels and then being done with it and then moving to the right and grabbing the next box of pixels and so forth. Don't reuse any of the pixels twice. Okay, you're going to need to start in the bottom left corner and work row by row, left to right and bottom to top to do the scaling properly. If you start in the wrong position or you don't move in the right direction, then you'll get a different result than us and you won't get your points. So please do that just as was described here. Now, depending on the dimensions of the original image, you might not have 4 pixels to work with when you reach the right and top edges of the image. In these cases, use what is available. So compute the averages based on the right side, you might end up with 2 pixels stacked vertically to work with, and on the top edge, you might only have 2 pixels sitting horizontally side by side to work with. It's also possible that by the time you get to the upper right corner of the image, that there's a lone pixel floating here, and in that case, just copy that pixel into the filtered image. So again, if this was a 3 by 3 image, then when we first worked across in this direction, we take all 4 of these, average those into a single pixel, and then we'd slide to the right to grab, and there would only be 2 pixels left right here. And so we would use those pixels to compute the second pixel on that first row. Then, when we tried to go to the next row up, there would only be the row of 3 pixels, because remember we said it was 3 by 3. And so for the first square that I tried to do, I'd find that I only had 2 pixels available instead of the 4, so I'd average those together, and then when I got to this, moved to the right, I'd find this lone pixel sitting by itself, and that would become then just copied into the final image. So my final image would be 2 by 2, so I hope that made some sense. If not, please feel free to ask questions of myself and the TA. Okay. So from the command line, then what should this look like? You already saw me run it, but if I was working with an image called hat.bitmap and I wanted to convert it to grayscale, I would type the following in the command line, and the output would be a file named filter.bmp. Now, a few hints. Do not try to do this entire lab at one time. Start by verifying that you're able to, for instance, open a BMP file and correctly read and identify the different pieces of the headers. And in fact, I would hit those different pieces one at a time. First, try to handle the BMP header and make sure that you can read that and write that correctly, and then move on. You have tools at your disposal. You know how to use XXD. You have your own version of it by now. And so you could look at the original file and look at the file you are creating and make sure that those bytes match up. And I suggest that you do that for each of these pieces as you work through, instead of trying to hit it all at once. Once you're handling the reading and writing of headers properly, then I would hit one of the simple filters first, such as grayscale or threshold, then get the other one working, and then finally do scale down last. Okay. Use structs wisely. I suggest using a struct for storing the 3 RGB values for a single pixel, and I suggest building more complex structs that incorporate sets of pixels for the pixel array and so forth as you move forward. It's also probably a good idea to have 2 2D arrays to work with when you're doing the filtering of the image. So one will be the array that contains the original data, and the second will be the array that contains the data for your filtered or target image. That'll especially make things easier when you're dealing with different sizes of things. So that's a tip for you. Okay, now though it is possible, we do not advise that you use exclusively fscanf or fprintf in order to complete this lab. we suggest learning about and using fread and fwrite, which are better suited for reading groups of bytes from a file into memory. So here's some example usage. So here's this variable number of elements read. When we call fread, it will tell us how many of the elements of a given size that we've successfully read, and it will return that from the function call. So we can store that and then check that variable to see that we read as much as we expected to, and so forth. So this basic syntax for using it is to call the function. It expects to have an address to a variable, and this is the variable where you're going to store the data that you're trying to read, the size of the thing that you're trying to read in bytes, and then the number of those things that you're trying to read. So this address, this variable that we have an address to, I should say, this could be the address of an array of pixels, for instance, that we might be trying to read in a pixel, which is going to be 3 bytes, right? R, G, and B values. And then we can say how many of those we're going to try to read. Finally, the last argument is going to be the file pointer that we're trying to read from. Similarly, then there's an fwrite function, which works in very much the same way. The difference is just the direction that we're going. We'll be reading from the variable instead of writing to it, and writing to the file pointer instead of reading from it. Don't do everything in a single function. I don't suggest just trying to read everything from the headers and read everything from the pixel array and all of that in one giant function. Break this into pieces and hit those pieces one at a time. Okay, so for instance, create a function that reads a pixel, create a function that reads the header, and so forth. Do not try doing this. It looks like I reset my numbering there. That's too bad. Do not try doing this all with your fingers on the keyboard. Draw some pictures and take notes of your thoughts. Think through this and how you want to architect your code, and then try to code it up. This will save you a lot of time. Start early, start as soon as possible, and ask questions when you have them. And as we come up with, if we notice people asking consistent questions and so forth, then we may put more hints and additional information here. So check back periodically. How will you turn this in? So we've provided you with a make file that you can use to do that. I'm going to let you read through this on your own, and I'm going to jump down to how you'll be scored. So there are basically 4 criteria we're going to look at. First, are you able to read and write valid BMP files? So even if your images don't look right, but they are valid, we can open them and look at them and so forth, you'll get 5 points. And you'll get 15 points for each of the 3 filters that you need to implement. Please pay attention to things that are highlighted. They tend to be important. Extra credit. We've given you two ways of getting extra credit. One is to format the name of the output file generated by your program so that it incorporates the name of the input file. So for instance, if it was called hat.bmp, then the result should be called hat_filtered.bmp. So that'll get you 2.5 extra points if you manage to do that. And then also to encourage you to not try doing this all at once in one gargantuan file, if you break your code into source and header files, multiple source and header files that represent the pieces of this program as you've broken it up, then we'll also give you 2.5 extra points. Okay, so that's fairly significant. We've also given you some images to work with. So firstly, I've given you this very simple face.bmp file. That's that just kind of ridiculous looking tiny bitmap file. I guess I'll pull it up here. Yes. Okay, that's just this simple itty bitty bitmap right here. And the whole purpose of giving you this is so that there's something small enough that you can actually look at the data kind of pixel by pixel in a reasonable amount of time to be able to diagnose problems and so forth as you're getting started. Okay, so so there's that you can use as you're just getting fired up. We've also given you an archive of 3 files, normal, buffer, and offset, that have different attributes that our test images will be looking at. And so this tar file contains these 3 images as well as the result of applying the filters to them. So you have kind of a before and after that you can use to compare the results of your code and make sure it's heading in the right direction. Okay, so at a high level then, that is the lab. I wanted to also give you just a few more hints by showing you, I'm going to jump here, pixel, showing you a few ideas that I used in my implementation just to maybe um, get you off on a good, on the right track, to a good start, so to speak. So I did as I suggested, and I used structs to kind of embody the ideas of the different pieces of this bitmap file. And so here you see I have created a pixel struct, and I'm simply storing 3 chars as unsigned chars, so each one's a byte, and will be interpreted in an unsigned fashion. And I've also in this .h file then defined 2 functions, read pixel from file and write pixel to file, that are helper functions that I'll use to get harder tasks working down the road. Okay, so I probably shouldn't be so generous, but I'm actually going to show you these. So here's my pixel.c file. No, I'm not going to give you this file. This is just to give you a glimpse of how you might approach some of this. But so here you see that all read pixel does is it takes an input file and the pixel that I'm trying to read into, and it tries, in this case I'm using fscanf, to read the values for that pixel, and then based on the number of things, based on the return value from fscanf, I decide whether or not, I'll scroll over just a little bit there, okay? Then based on that return value, I decide whether or not to say that this was a successful read and so forth. Same kind of idea on the right to pixel. So my purpose in showing you that is to really reinforce this idea that I'm trying to convey of breaking this down into manageable bytes, okay? There's my pun for the day. Break this down into small pieces that you can think about easily, manage those pieces, and then work up. Because then you have tools that will make it easier to think about the larger pieces. So for instance, having addressed the notion of a pixel, that's going to make it a lot easier when I'm actually trying to handle the pixel array. Okay, you notice I also have created header files for the different types of headers in the image, or the different pieces of it. So here's my BMP header.h file, and I'll show you this as well. Again, I think I'm being generous here. I hope you feel the same way. And so you can kind of get the idea where I'm heading with this. I've defined the struct that will store the data, and then I've also created a couple of helper functions that will both read and write the BMP header from and to a file. Both of these return a Boolean value, and this Boolean value represents whether or not we successfully read or wrote that header. And now this is a good thing to do because this allows me to, at each step of the process, when I'm reading in data, processing it, and trying to write it, and so forth, to be able to check and see, did I do that successfully? Did I do that successfully? And when I was developing this, it was very useful because I could see where things broke, when they broke, and it made it a lot easier for me to find the problems and debug my code. Okay, I think that's as much of a hint as I want to give you at this point. That's quite a bit of a hint, and so I'm going to leave it there. Again, please get started on this early. The sooner that you're pounding on it and making mistakes, the sooner you'll be able to work through those mistakes and come up with a finished product. Wish you all the best of luck. I hope this is challenging but also enjoyable to you, and that it's a good learning experience, and I look forward to seeing you on Thursday. Thanks, everyone. Bye.